ICTP under the supervisor of Professor Marcos Aguiar. And today I will talking about some preliminary results of the works that we are being developing here, which is called the influence of external drives on the frustrated Kuramoto model. Okay, so just to start, synchronization are widely occurring phenomena on the nature. I believe the most two talk examples are the fireflies flashing on the forest at night, and those of the metronomes that, when you're supported by a moving plate, they synchronize the ticking after a while if this plate is unstable. But there is a certain, let's say, class of synchronizing phenomena that's regarding external driving, in which I have a certain dynamic and I have a driving force that forces this internal dynamic to synchronize with the external one. For example, we have a lot of biochemical reactions that happens in the body that are synchronized with the natural rotation of the Earth, which we call circadian rhythm. And we also have some certain events on the neuronal networks that are driven by external stimuli. For example, the signaling via the optic nerve. So it's really interesting to investigate this kind of model when we're trying to understand all those kinds of phenomena. Okay, I will review some results that we will need for this work. First, by describing the original Kuramoto model, in which we have a certain population of oscillators, which are described by those phases, and each one of these oscillators has a natural frequency omega that is drawn by usually a symmetric distribution. We have a dynamical equation and a coupling amongst those phases, in which the intensity of this coupling will be measured by this parameter k. And to measure the integration of the system, we use this complex order parameter z. In particular, the module of this parameter will give us the size of the synchronization. And when we vary this the local coupling of the oscillators, we get this second order phase transition, in which if this parameter is small enough, all the oscillators, they oscillate in their own way, but after some certain threshold, we have this transition, and all the system behaves in a coherent way. Okay? But when we pick the same model and we add an external drive, an external periodic drive in this case, we are not interested anymore in the synchronization of the dynamic itself, but we are rather interested in the mutual entrainment between the external force and the original synchronization without this external driving. So to analyze this kind of systems, many times we use the Ott-Antonsen ansatz, in which we can write equations for the order parameter, both the module and the phases of this order parameter, instead of writing equations for each oscillator. Okay, so we can reduce the dimension of the system from n to 2 equations. And by analyzing these equations, those authors in the paper by 2008, they classified majorly two happenings that will occur in the system. We have this diagonal here, and if the parameters of the force are above this diagonal, the system will synchronize with the external drive. And if I have this region, E region here, the system will stay synchronized in their own dynamic. So what matters here is when the system will synchronize with the external drive, and when the system will stay synchronized in their own way. Okay? Well, the generalized frustration Kuramoto model or matrix coupling Kuramoto model was developed in this paper in 2022. And I will take some time reviewing this model because there are a lot of details here. But to ease the interpretation, let's consider, instead of describe the Kuramoto by phases, let's just consider that we have vectors oscillating in a d-dimensional plane. In this case, a circle. So instead of thinking on phases, we're thinking on vectors, and we can rewrite the Kuramoto equations in terms of these vectors. And by rewriting this, we can interpret the coupling as a matrix. Okay? And when we write the equation in this way, we can parameterize this matrix coupling as a sum of a rotational matrix and a symmetrical one. And if you write in this way, we can recover the original angular formalism in this equation that combines a lot of previously studied models. For example, if I set J equals 0, I recover the Kuramoto-Sakaguchi model. So this model is extremely general, and it contains a lot of previous work within it. Yeah, it's a vector rotating on. Okay, and the oh. No. This is a vector rotating on the circle, and the omega is an unsymmetric matrix that represents this frequency, this natural frequency here. Not necessarily, but okay. Yeah. This matrix contains this omega here. Is an unsymmetric matrix that when we do the calculations, we recover this formalism. No, but this omega is a matrix that has only two entries that correspond to this little omega here. I forgot to come. No problem. Yeah. Which plus? Yeah, here. Yeah, but not in this case. So we're not. Yeah. Yeah, we choose as a Gaussian distribution around some certain mean that could be or not 0. In the end, this term will be relevant because it's because of this J that the new synchronization modes occur in this model. Usually we set the variance to 1 without loss of generality. May I proceed? Okay. Okay, so we have this equation and the phase diagram of this matrix coupling model. We arrived two new synchronized forms. The first one is this pinkish region, which we call oscillatory, because both the module and the phase of the order parameter, they oscillate in time. So because of this J, we have a certain frustration on the system. We have a preferential direction that the system accelerates towards them. So we have a oscillatory synchronized state that is not uniform more in this region. And in this pink region, in this green region, we have what we call the phase-tuned state, which we also have this preferential direction that the whole system locks onto this direction, even this natural frequency is different than 0. So we have the breaking of the rotational symmetry, and we arrive with these two new synchronized states. Here in blue, it's the disordered state. In those diagonals, we recover the original Kuramoto model. And when we set J equals 0, it corresponds to Kuramoto-Sakaguchi model. Okay? So this is the model that were proposed in this paper in 2022. What we are interested in studying is how the external drives will change the dynamic of this model. Okay, so we can construct these equations that are really complicated to solve analytically because they depend explicitly on time. So they are non-autonomous. We need to perform numerical calculations to investigate how these external drives will affect the dynamic. And what we observe in this first case, we set the system on the oscillatory state. So we have a small j with a natural frequency rotation of half, and delta equals 1, which is the width of this natural distribution. We perform some numerical integrations for several values of the intensity of the external drive and frequency of the external drive. I don't know if the image is good, but can you see some stripes here? There are some subtle stripes on these regions. During these calculations, during these integrations, we calculate the time average order parameter. It is worth to remember that in the system, there are high levels of synchronization in all cases. But the subtle differences between those stripes indicates that have some certain different dynamics that are occurring here. Of the colors? Yeah, it's scaling about 85 and 84. 84, it will be the most close to black, and 0.85 close to white. Okay, it's really subtle in this case. So we try to calculate other stuff in order to investigate what's happening in those different regimes. And what we find by calculating the Poincaré maps within and in the exterior of the stripes, that when the external drive completes one lap, I mark the point in which the dynamic of the system is in the torus, in the space. And within the stripes, we see a small number of points, 1, 2, 3. And when we are in this region, the Poincaré maps, they are the components of the order parameter. Yeah, and then P cosine phi and P sine phi. You calculate Px and Pi. Here, we have the P and Y, P and psi, and P cosine psi is Px. Yeah. Okay? So we can, we see these different regimes, and when we perform a cut on these diagrams here and calculate those points, for example, Px, we observe those different regions in which the Px ranges for, let's say, infinite points, aperiodic orbits, and we have small or larger regions in which Px have finite periodic orbits of period 1, 3, 5, and so on. Okay, so we also calculate the winding number in the system, and we observe these certain plateaus that correspond exactly to the width of these stripes. These shapes are called the devil star cases, and we also calculate the period on each of the stripes. You can see that we have orbits of period 1, period 3, period 2, period 5, and so on. Here is just a zoom on this region. Okay, so this kind of shape, which are called the Arnold tongues, they indicate that this model, they have a more complex entrainment with the external drives than simply the coupling with the external drive. The system may couple in an orbit of period 2 or orbit of period 3, and so on, which does not occur on the usual Kuramoto model. Okay, so to the final remarks, this matrix coupling Kuramoto model, they exhibit novel and interesting new synchronized states, and by adding this global external drive, we can obtain these dynamical equations, but we cannot solve this analytically. But when we solve this equation in numerical terms, we can observe the formation of these Arnold tongues and mode lock regions in a ways that the usual Kuramoto, that were not possible in the usual Kuramoto model. And the next step is to investigate the phase tune region, in which all oscillators are tuned on a given direction. That's all. Thanks for your attention.
We have time for one short question. Yeah.
Guilherme, thank you very much for your very nice talk. But by the way, I suggest that you have you do the similar thing for the Stewart-Landau model. Because for the Kuramoto model, you're truncating. So what you call Kuramoto model is a truncation of the model.
Yeah.
If you do not truncate, then high order terms will appear, and they can lead you to higher order Arnold tongues.
Okay.
Yeah, so if you do, like, instead of the phase reduced, do the full blown periodic orbit, it would be very nice to compare.
Okay. Thanks for the suggestion.
Well, thanks again, Guilherme.